welcome everybody. My name's Carrie Monohan. I am the program director at the Sierra Fund, and it's my pleasure to do this lunch and learn with you all today. We have a series of talks this spring inspired by Earth Day, and we have a list of these at the end, so we can help you get registered or at least make you aware of some upcoming talks that you might be interested in. At each Lunch and Learn, we're going to get more and more specific into more detailed project activities. So I'm still trying to stay at kind of a 10,000-foot level and introduce to you the Ecosystem Resiliency program itself. Great. So in 2007, the Sierra Fund launched a comprehensive effort to address the impacts of the California gold rush. That's really when we began this. The impacts of this resource extraction era resulted in a transformed landscape. We have the mines themselves that created scars. We have the forests that surround those mines that experience massive clear cutting to timber the mines and build the towns. The meadows were used extensively for livestock grazing. Barriers were built in streams so that hydraulic mining debris could be held back, and those debris control dams still block fish passage today. And of course, the impact on people that lived in the Sierra before the gold rush that were forcibly removed from the lands that they stewarded for thousands of years. So the program objective of our Ecosystem Resiliency program is to identify and fill data gaps so that we can inform policy and develop best practices. Our first program target is related to the mines themselves. We had both hydraulic and hard rock mining. There are more than 40,000 abandoned mines in California. Mercury was mined in the Coast Range and brought over to the Sierra to be used in both hard rock and hydraulic mines. So this map is giving you a depiction of the state and how many hard rock and hydraulic gold mines there are with the gold dots, and then where those Mercury mines were in the Coast Range. Hydraulic mines are characterized as active erosional areas. It has to do with how they were created with water cannons. They were often worked over during several different time periods and then abandoned. They tend to be very complex sites. We can find drain tunnels sometimes on these sites, remaining ditches, gullies, ponds, and they typically have multiple outflow points. So when we began this work at looking at the mines, we were faced with this: where are they all? Are they all in the middle of nowhere? And does anyone still care, basically? We were faced with this perception that maybe all of the mercury had washed out. And then this overwhelming concept that what could we do about it anyway? If we had so many mines, they were in the middle of nowhere, all of the mercury washed out, what is it that we can do about it? So we addressed each one of these different data gaps with our pilot projects. One of the major developments that advanced this work is the use of LiDAR, which allowed for the identification and mapping of these sites. So with LiDAR, we could see the area that was exhumed by hydraulic mining. And so that's these polygons that are drawn around these scarred landscapes that you can see. You can see how much harder they are to see at the aerial photography. With so much growth, for example, and greening that we have, it's hard to identify where these hydraulic mine sites are. So LiDAR really changed all of that, right? The other thing that LiDAR allows us to do is we can create digital elevation models using GIS, and we can actually calculate the volume of material that was exhumed, and in fact where it was emplaced and deposited in these upper reaches. So right between these two polygons here, you can see this large slug of hydraulic mining debris just sitting in these lower order stream channels that hasn't had the power to wash out. So that really myth busts the idea that it's all washed out and there isn't any left. these sites are still eroding today. And in fact, we have these large deposits that don't have the stream power to move them. So let's just talk a little bit about how mercury was used at these hydraulic mine sites and what took place there. So you can see a picture of a hydraulic monitor. This is largely used to power wash away the hillsides and excavate the material, which is then shunted as a slurry into these sluice boxes. They look like troughs there. And in those troughs, mercury was added. Mercury would bind to the fine grained gold, creating an amalgam that then would settle out, and when the water was turned off, then that amalgam could be collected. The mercury would then be volatilized, captured, and reused by the mining operation, and they would have the gold there. The thing is that there's an estimate of like 26 million pounds being brought over from the Coast Range to be used in the Sierra Nevada for both hard rock and hydraulic mining. And from that, at least a 10 to 30% loss rate to the environment. So I think these pictures really help us see just how messy that process was and how loss to the environment could happen pretty much at any stage here. We know how much mercury was brought over because it was really good record keeping by the businesses, by the mines themselves. It was a very expensive thing that the mines had to purchase. And so it's better understanding how it was used and that we can better look for where mercury might be today. This is a picture of iconic site most all of us in Nevada County have had the privilege of enjoying. This is Malakoff Diggins. It was once the largest hydraulic mine in the world, and in fact the place that this technology was used at first. So it was a fairly large mine site. It's what I call a beautiful disaster. We can see the Bryce Canyon-like cliffs and all of the active erosion that's going on there. And Sierra Fund has an entire talk to give on this site itself. We started assessing it in 2011 to see what issues are still continuing at this site and how we could work better with state parks to address some of those issues going forward. So the coolest thing about Malakoff is that it all drains out one location at the Hiller Tunnel. And so this is us taking samples during storm events at the Hiller Tunnel, at the stream above the mine site, and then down below where the tunnel and the stream collide, so where Humbug Creek and Diggins Creek converge. And you can see the color of that water, this Thai iced tea-like color that we actually see during big storm events. So what was new about this work is that we started looking for mercury at low levels and during storm events. And what we found was that it was this one form of mercury, which we refer to as particulate bound mercury, which really came out of these mine sites. And so we have, particulate bound mercury is defined as if you have an unfiltered sample from that storm event and a filtered sample, and they're both run for total mercury. The difference between those two is what we call particulate bound. And these are some scanning electron micrograph pictures of mercury on a piece of amalgam, but I imagine this as mercury associated with silts and clays. So if you had a clay particle the size of a whale, mercury would be like a cherry on top. So it acts like clay, it acts like silts and clays. It's in suspension and it's easily transported really long distances. So this new understanding of mercury, where it's coming from, the form that it's in, really helped advance our program. So to summarize what we have, our major findings at this time was that with LIDAR, we can identify and inventory where all of the hydraulic mine sites are, and in our minds be pragmatic and prioritize them for restoration activities. Mercury certainly did not all wash out because we started taking samples during storm events, and we understand that these hydraulic mine sites are still sources today. And in fact, by understanding the form of mercury that's coming out of these mine sites, it can inform what we can do about it. So controlling particulate bound mercury is akin to controlling the fines. So you can filter them or settle them and reduce the amount of discharge to downstream waterways. So moving on to meadows in the Sierra Nevada, there's over 19,000 meadows in the Sierra covering more than 280,000 acres. And about 40 to 60% of them have been degraded by human activity. So this diagram gives us a conceptual model of a degraded meadow that has an incise stream that is not connected to the floodplain. And this results in the desiccation of what was once a wet meadow. So you have dry plants, sagebrush dominating the meadow environment. Whereas before, we had a stream that was in contact with its floodplain and the water table was high, and we have more of a wetlands-like environment. So with the resource extraction era of the gold rush, with the unregulated grazing that took place during that time, a lot of streams were literally trampled to death, if you will, trampled so much so that that compaction resulted in this incision. And we still see this today in many meadows, and we know more and more about how to correct it. So there are many benefits to healthy meadows. They can improve the water quality. They can increase late season flow. That colder water is one of the key aspects of a hydrologically functional meadow. I think it's obvious that these meadows provide critical habitat for many forms of wildlife, and they also are working landscapes and provide important forage for grazers. It's important to point out that there's some unique characteristics of high elevation wet meadows where they have high net primary productivity and seasonally low temperatures, as well as saturated soil, which make them really prime candidates for soil carbon sequestration, especially below ground. So understanding the function of high elevation wet meadows in soil carbon sequestration is a really fascinating piece of research that we'd like to continue with. So the data gaps that we've identified as a part of our meadow restoration program is, can we create standardized protocols for monitoring the effectiveness of meadow restoration so that we can compare it across the Sierra, what's working, what's not? Is there in fact enough carbon to offset the costs of restoration? And perhaps most importantly, how do we improve stewardship and engage local communities in meadow restoration efforts? So we've been working with this amazing group of meadow restoration practitioners, and what we all know is needed is a standardized way of measuring and evaluating meadow restoration efforts so that we can compare them across this wide region, what restoration activities are working well where, and improve. We meet regularly as a technical committee to work on these protocols, these standardized protocols that could be used for a wide range of meadow restoration efforts. And we hope to be releasing early protocols this spring that then could be tested, in fact, this field season. And in the future, perhaps even offer trainings for how to implement these protocols. This is obviously an iterative process and will continue to change and evolve as it goes forward. So our primary meadow restoration pilot project at the Sierra Fund has allowed us to develop and test many of these protocols. This is the Clover Valley Ranch, and there are numerous grade control structures that were installed as the meadow restoration technique, and also beaver dam analogs that were installed as the meadow restoration technique. These essentially do the same thing, which is halt that incision process. But how well do they do it, and what is the response time? So we've set up a series of shallow ground monitoring wells here. We have avian surveys taking place here. We took a range of soil cores. We have 3 different stream gauges at this site so that we can measure that sponge effect of the meadow as it restores itself over time. And this is the site in which we're embarking all of this, and a future topic of one of our talks. We also have an annual field camp at Clover Valley, and we've done this with the Maidu Summit Consortium. It is really amazing to bring Maidu youth out to Clover Valley during this 1-week intensive where we include them in the field work that we are doing and expose these youth to careers in natural sciences. But even more importantly is the information we get back from them and from the elders that are part of that field camp. They're helping to inform our revegetation list, for example, and we call this traditional ecological knowledge. So this is the stewardship piece that we're talking about. In fact, these were their lands for many, many thousands of years, and it's just really fabulous to get to be a part of pulling this back together in some way. So to summarize where we're at with our Meadow Restoration target, part of our ecosystem resiliency program, is that we are working with the Sierra Meadows Partnership to develop these standardized protocols. With respect to the carbon question, it's definitely still out there, but we are working with carbon market economists to try and define a crediting rate for ranchers that might incentivize them to do more restoration. Right now, it looks like that the carbon markets are changing very quickly, and there might be a way to get some of those ranchers interested in having less cattle on the land if they can benefit from having carbon offset some of those costs that they have for maintaining that property. And then our piece around stewardship and engaging local communities has everything to do with our field camps and working with the Maidu Summit Consortium. So our third target as part of the ecosystem resiliency program here at the Sierra Fen has everything to do with forestry practices and management. So the Tahoe National Forest was the epicenter of the gold rush, as with some of the most extensive gold deposits, and it is a huge forest. It's over 800,000 acre forest, and there are many hydraulic and hard rock mine sites throughout that forest, but there's also really high fire severity zones in this area. And so our questions around this are, how do we promote forest health, not just fuels reduction itself? And very specifically, can hydraulic mines be included as a part of these forest health projects? And importantly, can we create a financial mechanism that would allow for mines and meadows to be included in forest health projects and financing some of those larger projects? So for this, we have the pilot project as part of the Trapper project. This is a large fuels reduction project that the Tahoe National Forest is currently permitting. It's about a 31,000 acre planting area, and over 19,000 acres are in the National Forest System. The Tahoe National Forest has identified a number of different objectives for this effort. It includes forest health and resilience to changing climatic conditions. It includes reducing surface and ladder fuels. It includes protecting or improving wildlife habitat, and of course, maintaining and improving watershed and soils conditions. So the map that I'm showing you here is a map we helped create with them to identify the location of the known hydraulic mine sites within this boundary, as well as some of the other treatments that the Forest Service has proposed. So the idea of coupling hydraulic mine remediation with forest health is very simply put by saying, if you're in there already, doing forest health projects, can you do something to help remediate that mine site? So could you slope back eroding areas? Could you provide chips to those sites? It's a multi-benefit effort. So to test this, this great idea and really put it into action, within the Trapper boundary, there's over 70 hydraulic mine sites, right? And we identified 2 of them. One is called Tippecanoe and the other is called Grizzly Creek. And we got a Sierra Nevada Conservancy planning grant to go through the environmental permitting needed to design remediation plans for both of these sites. So down here, these last 4 bullets at the bottom are maybe the important ones and what we're learning along the way, in that we've had an archaeological survey at each of these sites to determine whether or not they're eligible for Section 106, so whether or not they have cultural resources that are of significance. We've done some stormwater sampling at these sites to see where contamination might be coming from, so that's the low level stormwater sampling for mercury. And then from both of those efforts, we're able to create a remediation design. And the key to this is integrating both the findings from the cultural and environmental assessments. Yeah, so those are our pilot projects for hydraulic mine sites within the forest. So where are we at with this? we're trying to figure this out. I mean, that's all of this is in process. So we have these pilot projects. I think a really great outcome would be best management practices, some sort of programmatic permitting for all hydraulic mine sites, so that we could say, if you have an eroding cliff of this type, it can be sloped back to this angle, chips can be added. Another really interesting amendment that hopefully will become part of these pilot projects is the use of biochar on these sites. Biochar has the ability to adsorb mercury, specifically particulate bound mercury, but also dissolve mercury. And those might be really meaningful additions to reducing the amount of discharge from these sites. And then with respect to the financial mechanism, right now there's this new model, it's called the forest bond model, where it's really increasing the pace and scale of some of these forestry efforts by pulling together funding sources from downstream beneficiaries, allowing projects to get going right away on the ground, and then reimbursing those the beneficiaries, or reimbursing the bond with multiple funding streams that come in from different times. And so the idea is that could we add carbon or reduce sedimentation to this model? And that would mean maybe we could have meadow restoration as a part of forest health projects, and mine remediation as a part of those as well. So our last target that I want to mention to you today is about our efforts to restore volitional fish passage in the Sierra Nevada. There's 14 foothill dams in the Sacramento and San Joaquin rivers, and these are all preventing the migration of anadromous fish. The Yuba River is really an interesting case study. It has been identified as the best opportunity for the recovery of endangered Central Valley spring run Chinook. And what you're looking at there is Englebright Dam. It, in fact, is a debris control dam that was built so that hydraulic mining could resume. And so its sole purpose is to hold back hydraulic mining debris so that it wouldn't flood the farms. And that was a big thing that changed around hydraulic mining, is that it was allowed to resume as long as the material was held upstream. Well, now we have this piece of infrastructure that was put in place for something to start back up a really long time ago. Hydraulic mining did not resume as we had hoped. So what function is Englebright serving today? And can we maintain that function as well as bring anadromous fish back up into the Yuba River? So specifically, the two different data gaps that we're trying to look at with this pilot effort is there enough habitat for salmon in the Yuba? And what can be done with all of that sediment behind the dam? So the first thing we did is look at all the studies that were already out there about habitat in the Yuba River for salmon. This is something that's been looked at for a really long time. But we realized that the temperature monitoring devices that had been installed previously were installed in easily accessible areas like road crossings at bridge sites, like specifically Bridgeport, where it's very shallow and you might take your toddler swimming there. Well, that's convenient for somebody who's driven a long way to install a piece of equipment, but then that data was being extrapolated for miles and miles of the South Yuba, and we were getting not very precise data. We were getting information that it was all too warm. So what we did that was different is that we targeted our data collection effort to be from pools that were previously identified with these temperature monitoring devices, or tidbits here. So we went to all of these different pools that we could access, installed these tidbits throughout the warm summer months, and started collecting data. So that's the beginning of a longer effort, but we are finding that there is plenty of cold water refugia, especially in the middle Yuba. So to address that other data gap, we've been working for a long time at this issue of reservoir sedimentation. This is a picture of greenhorn that comes into Rollins Reservoir, taken from a helicopter, and you can just see that's all hydraulic mining debris that's still coming into the reservoir. So if you own a reservoir in the Gold Country, you have to deal with sedimentation. And so if you want to keep your reservoir storing water, regular maintenance activities need to take place. Now, how do you do that in an area that has a legacy of mercury contamination? So this is a profile of Englebright, in fact, from a USGS report. And if you could just imagine that blue line moving from 160 here, feet in, or meters in elevation down to something like 140, and then carry that across, what you would see is that a whole lot of sediment would be exposed in the dry. So if that sediment is in the dry, then you can remove it with earth moving equipment. And that's what you see a picture of here happening at Combi Reservoir. It's inexpensive to remove sediment in the dry. It doesn't create the water quality problems that removal in the wet might. And by lowering that at Inglebright, we would be able to install a volitional fish ladder at that elevation and still maintain that facility as an after bay to New Bullards Bar. So we're looking for those win-win-wins so that we can move forward. So this is where we're at in this effort. So we're identifying cold water pool habitat, and of course starting to understand a programmatic approach to addressing sedimentation in reservoirs across the Sierra Nevada. And it might even be a way to create sellable aggregate from these efforts. So with that, I have summarized as quickly as I could, certainly not 15 minutes, 4 different areas of our ecosystem resiliency program and how we identify and fill data gaps that inform policy and hopefully are used to be able to create best management practices. Our wonderful board and staff, this is all of us social distancing, doing field work in early March at one of the hard rock mine sites we are assessing. So I just want to invite you to join us, consider supporting our work, and please continue to participate in these lunch and learns. And with the rest of the time that we have together, I welcome a discussion and any questions that you might have. Thank you so much.